In the last video, we talked about how the BICEP2 team seems to have discovered specific patterns in the polarization of light from the cosmic microwave background, which could have been produced by strong gravitational waves in the early universe. But where did these gravitational waves come from? Let's go back to our picture of the Big Bang. From our observations of galaxies moving away from us, observations of the cosmic microwave background, the large-scale structure of the universe, the abundance of primordial elements that were produced in the Big Bang, and from what we know about particle physics at these energies, we have solid evidence for what the universe looked like going back to about 1 second after the Big Bang. And we can extrapolate a little bit more, but not too much more than that. Now, in the late 1970s, while scientists were beginning to understand more and more about this picture, many scientists were struck by how remarkably flat the geometry of this very early universe would have to have been in order to lead to the kind of universe that we see around us today. This was known as the flatness problem. There was another issue that scientists had with the cosmic microwave background. Why does the entire cosmic microwave background look so uniform in temperature, even though parts of the cosmic microwave background that are on opposite parts of the sky should have been so far apart that they should never have been able to communicate with each other? How would they transfer any heat between each other to reach this very, very smooth temperature? This was known as the horizon problem. Well, it could just be the case that the universe just happened to start in this exceedingly finely tuned state. But that didn't satisfy most physicists. So in 1980, Alan Guth hypothesized that if immediately after the Big Bang, about a trillionth of a trillionth of a trillionth of a second after, the universe went through a brief period of exponential accelerated expansion, or inflation, then a couple of things would happen. First, the geometry of the universe, even if it wasn't completely flat here, inflation would flatten it out automatically. So you would solve that issue of the flatness problem. Second, the points in the pre-inflationary period would have been close enough together to reach the same temperature, and then inflation would separate those regions, so you can have those very separated regions on the CMB that have the same temperature, so it solves the horizon problem as well. Another aspect of this theory is that quantum fluctuations would prevent the universe from completely smoothing out. This inflation would smooth out a lot of it, but there would still be quantum fluctuations that you couldn't get rid of. And these quantum fluctuations, as the universe continued to evolve, would eventually become the density fluctuations in the cosmic microwave background that eventually formed galaxies and stars and clusters of galaxies. So this inflation theory also offers a source of these tiny fluctuations in the cosmic microwave background as well. So this theory of inflation was quite promising. It was a single mechanism that seemed to solve the flatness and horizon problems, as well as accurately explain where the first density perturbations in the universe came from and their properties. And since then, much research has gone into developing plausible models for this inflationary period and understanding the possible properties of a field which could drive this inflation. However, this research has largely been based on theory. Although viable models of inflation have to lead to a universe like the one we see, the energy scales at which inflation occurred were so high, many magnitudes higher than can be reached in any particle accelerator, that it's difficult to test these models. But there is one prediction that these inflation models make, that during the time of inflation, there would also be quantum fluctuations in the curvature of space-time itself. And these fluctuations would produce strong gravitational waves in the very early universe. And as the universe continued to evolve, these gravitational waves would pass right through this hot, dense plasma and still be around when the cosmic microwave background formed. And as we talked about in the last video, gravitational waves will imprint specific E and B mode patterns on the polarization of the CMB. The specific strength of these B modes depends on the strengths of the gravitational waves that were produced, and the strengths of the gravitational waves depend on what the properties of inflation are. So to kind of summarize what we're trying to do, in inflation, we have a whole bunch of different models that we've come up with that kind of have the basic properties of inflation, and those make different predictions about what kind of gravitational waves we would get. The strength and property of these gravitational waves determines the properties of the B modes in the cosmic microwave background, and that is the signal that the BICEP2 team was trying to measure. Working backwards, these B modes tell us something about the gravitational waves in the early universe, and that not only gives us strong evidence for inflation overall, but might help us identify which of these models are correct and which of these models have to be thrown away. So this measurement of the B modes in the cosmic microwave background really gives us a unique view at the first moments of the universe, because again, this inflation period occurred about a trillionth of a trillionth of a trillionth of a second after the Big Bang. Now, we still do have to be careful. In any physics experiment, and especially one as sensitive and precise as this, there is always the possibility of some sort of systematic error or some sort of false signal being able to enter into the data that you've gathered. And this is no exception. For example, one known source of a false B-mode signal is from the cosmic microwave background being gravitationally lensed by large galaxies. So what that means is, we said that density perturbations in the early universe could only produce E-mode patterns in the CMB. However, the light that carries that signal has to propagate through the entire universe in order to get to us. And sometimes that light will pass by clusters of galaxies, which can gravitationally lens that light and turn those E-mode signals into B-mode signals. And this was actually detected last year, so it is a serious concern for anyone doing this kind of a measurement. And there are other sources of possible error with interstellar dust affecting the results, or unknown systematics in the telescope. So let's take a look at the results that they posted and see how they addressed some of these concerns. So once again, we have the B-mode map that the BICEP2 team found in the CMB. And to check that this was actually coming from gravitational waves, the BICEP team compared their measured B modes to a simulated map of what you would expect to see if there were no gravitational waves at all and all of the B modes came from gravitational lensing. And you can see that the strengths of these B modes are all significantly smaller than the strengths of the B modes that they actually saw. They also considered different models of how interstellar dust and gas may have distorted these B modes. Each of these lines represents a different model for the dust, but their analysis suggests that these effects would be significantly less than the strengths of the B mode signals that they have detected. They also looked at the average B mode strengths over various angular scales on the sky. In this figure, the multipole number corresponds to the angular size of the B modes across the sky. Higher values for the multipole moment correspond to smaller regions of the sky. And this vertical axis corresponds to the strengths of the B modes on each angular scale. The dashed line on the bottom corresponds to the B modes that you would get only from inflation. The solid line corresponds to the B modes, the fake B modes that you would get from gravitational lensing from foreground objects. And the top line corresponds to the sum of those two. So we can see that although at very high multipole moments or very small angular scales in the sky, the lensing dominates, the detection that the BICEP2 team has made at smaller multipole moments or larger regions of the sky seems to correspond quite well with inflation. This R value that is posted here corresponds to the strength of the gravitational waves produced during inflation, And based on the strength of the B modes that were measured, it seems like the most likely value for our based on this data and this analysis is about 0.2. It could be a little bit more, it could be a little bit less, but it seems extremely unlikely that R equals 0 or there were no gravitational waves present in this signal. So what does this measurement tell us? Well, for a start, it gives very strong evidence that inflation actually did occur in the earliest moments of the Big Bang. The theory of inflation succeeded in doing what any good scientific theory should do. It made a new prediction for something that could be observed, and a group of dedicated scientists went to look for that signal, and in this case, we found it. Furthermore, the strength of the signal that BICEP2 measured, this R equals 0.2 value, is actually quite a bit higher than most physicists were expecting. With this information, theorists will look back at the different models of inflation and see which ones could produce a signal of this size. And this will, at the very least, narrow down which models could still be viable. The strengths of these B-mode signals also tell us about the energy scale of inflation. Over 1 trillion times the energy that can be reached in the world's largest particle accelerators. These observations give us a unique view of the physics that comes into play at these immense energy scales, and there doesn't seem to really be any other way of studying these kinds of energy scales other than understanding what happened in the very earliest moments of the Big Bang. Undoubtedly, other experiments that are looking for similar signals will continue their work and see if they can find additional evidence for primordial gravitational waves and inflation, giving us more information and a better understanding of our universe. In the coming months, as other groups report their results, it will be interesting to see how all of the evidence compares and what we can learn from it. This is a first detection, and if these results hold up, this could be considered the birth of gravitational wave astronomy. Thanks to the dedicated efforts of the BICEP2 team, we have opened up a new way of studying the universe around us, and as always, it will be exciting to find out what we learn next.